So far in your study of right angle triangles, the only tool you've used to examine the lengths of the sides of a right angle triangle is a Pythagorean theorem. And today what we want to do is expand your toolkit for being able to solve for not just side lengths, but also angles as well. And that first tool is something called the tangent ratio. And this is something that is only used for right angle triangles. So let's begin with something that you are already familiar with. Let's say that you've been asked to help design a ramp from the gym floor up to the stage to help with commencement or maybe assemblies, especially those who have mobility issues. And let's say that the height of the stage is 4 meters. Now please note, all of these diagrams are most certainly not to scale, and neither are the ones in your notes, but you'll get the idea because of how I've labeled them. Now we could have a ramp that's really long, let's say 22.69 feet long, with only an incline of 10 degrees. And for most of us, that would be pretty ideal. If you were in a wheelchair trying to wheel it up, that would be your most ideal scenario as well. If you only had the ramp starting, say, 8.58 feet away from the stage, it would end up being at an angle of 25 degrees. Not impossible to climb, but most certainly more difficult. And then finally, let's look at what if you had a ramp that went from the floor to the top of the stage, so close to the stage, in fact only 2.3 feet away, that it ends up being 60 degrees up. Well, no one's going to want to climb that one. Let's compare these three scenarios by looking at their slopes. And you already know that slope is equal to rise over run, or in this case, vertical distance divided by horizontal distance. So if we do 4 divided by 22.69, we could get the slope of that particular ramp. And we can do the same thing for the other ramps too. Again, just doing rise over run values. So if we calculate the rise over run for the first ramp, we find out that it's not very steep. It only has a slope value of 0.17 approximately. I'm going to take it to 3 decimal places though. Let's do 176. Let's do the same thing for the other 2 ramps as well. We get a value of, not surprisingly, a little more, 0.466. And these are all approximate values. I am rounding the decimals. And then finally, for the last one, we get 1.73. Pretty steep to try and have to climb. And we'll add one more decimal place in there just to be consistent. Let's make this a 2. Okay? Low slope, medium slope, high slope. What I'd like to do now is compare that with something called the tangent of the angle that this ramp makes with the horizontal or with the floor. So if we punch in tan of 10 degrees into our calculator, and I'll show you how to do that in a second, the tangent of 25 degrees, and also the tangent of 60 degrees, let's see what kind of outcome we get. I'm going to put it underneath here just for space reasons. So, to do this on your calculator, you're going to have one of 2 types of calculators. You're going to have the type where you can see what you're punching in as you go. So you're going to look for a new button that says tan on it. If you punch in tan 10, on my calculator I don't have to close the bracket, but I can. It will automatically give me an answer without closing the bracket. So it comes out to 0.167. Well, lo and behold, that kind of looks familiar, doesn't it? If you have the other type of calculator where you can't see what you're pressing in as you go, and I'll use my iPhone as an example, you won't see a tan button when it's in this orientation, but if you allow it to go into scientific mode, you will. And the tan button is here. If I try and punch in tan 10, it's not going to like that very much. So instead, I have to punch it in backwards. I have to punch in 10 and then hit the tan button, and I'll get the same answer that I did on the other type of calculator. Okay, so if we go ahead and finish the values for tan 25 and tan 60, let's see if we get some patterns here. Well, it looks like this one comes out to 0.466. Again, kind of looks familiar. And if we do tan 60, hey, also a familiar pattern. So what's neat about this particular primary trig relationship is that it's something that you already know. You know that the ratio of rise over run is something we call slope, But we can now see that rise over run is also equal to the tangent of this angle that is formed here between the hypotenuse and this horizontal line 2. So let's explore this in a little bit more detail. Let's jump down to example 1, and you can read through the big ideas to show visually what I've just talked about. So what we're going to do here is we're going to find tan theta for each of the following triangles. So in the first one, you have your right angle triangle with side lengths of 12 and 5 here that meet at the right angle, and 13 here, and theta is here. Theta is this funny little circle with a line through it. It is just a variable we use as an unknown when we're talking about angles instead of using x. And that way we can differentiate between finding unknown side lengths by giving them an x designation, but we can also talk about unknown angles by giving them a theta designation. So we realize that tangent has to be equal to something called opposite over adjacent. So what that means is that if I look at theta in particular, I'm going to look across from theta to see what the opposite side length is from that angle. And there it is, it's 15. I'd also like to be able to figure out what its adjacent is. And its adjacent is the side that is not the opposite, and it's the side that is not the hypotenuse. The hypotenuse is always opposite the right angle. So the adjacent is this one. I'm going to call it letter A just for short for adjacent, and I'll call this op instead of O because that might be confusing to do opposite. Okay, so for this angle, tan theta is equal to opposite over adjacent, and I'll use colors here just to show where everything comes from. So our adjacent value was 12, our opposite value was 5, and therefore the tangent ratio for angle theta is 5 divided by 12, and 5 divided by 12 comes out to 0.416 repeater. So we'll go approximately 0.416, and I'm going to go here to 4 decimal places when I'm looking at tangent ratios. We'll talk about that a little bit later. Let's practice this again with another triangle, orientated slightly differently, but still has the key features that we need. Notice where the right angle is. That tells you that the side opposite must be the hypotenuse. And we notice that the tangent ratio has nothing to do with the hypotenuse. We'll come and learn about some more ratios that do involve the hypotenuse in future lessons. Okay, so I'm going to designate this as being theta, and I want to know what the tangent ratio is for angle theta. Again, by definition, it is equal to the rise over the run, or the opposite over the adjacent. The opposite side, in this case, is 6.8. The adjacent side is the side that is not the opposite, not the hypotenuse. It must be this one here. There it is, with respect to angle theta. So the tangent ratio for angle theta is 6.8 divided by 4.5. which comes out to 4 decimal places, approximately 1.5. And my calculator has this little line going across it, which means it's ones from that point onward. So I'm going to go 1, 1, 1. Whoops, yeah, there we go, 4 decimal places. Decimal places, not digits, so how many values do you have to the right of the decimal? All right, last example. Same triangle, but what happens if, instead of choosing theta to be this angle here, what if we choose it to be the other angle that is not the right angle in this triangle? So let's put it here. What happens then? Is it the same or different to the triangle we just looked at? Well, again, by definition, the tangent ratio of an angle is equal to its rise over its run, or its opposite over its adjacent. So when I look at this angle, the side opposite to it is right here. It has a value of 4.5. And when I look at the angle that is adjacent to it or beside it, that is not the opposite and not the hypotenuse, the one opposite the right angle, I see that its value is 6.8. So, how does this ratio compare to the previous example? Well, it has the same values in it, but they're reciprocal. So it's not going to have the same value when you punch it into your calculator. So when you punch it in, you end up with a value of approximately 0.6618 to 4 decimal places. So to clarify, this is not the value of the angle in here, it is just the ratio of its opposite side to its adjacent side. We'll be able to use this though to eventually figure out how big those angles are in those three triangles. Okay, let's do some more practice with your calculator. I would like you to punch in tan of 0, tan of 35, tan of 45, and I don't want you just to write down my answers. I want you to find these buttons on your calculator. Tangent of 72 and tangent of 90. Okay? Go ahead, I'll race you. And again, we'll write them all to 4 decimal places unless I tell you otherwise. Look how quickly this tangent ratio grows as the angle gets larger and larger. These are approximate values, by the way, except for tangent of 0. Sorry, my bad, not theta. Now something very interesting happens when you try to take the tangent of 90. It gives you a glaring error. Why is that? Well, let's think again about what tangent really means. Tangent has to do with the rise over run ratio for a particular angle. So if we have the x and y axes here, and we think about an angle that is created from pivoting at the origin upwards all the way from 0 to through to 45 and up to 90, let's think about what this means. Well, tangent of 45 is an easy one to envision first because 45 is halfway up. That would mean that this side and this side are equal length. So any value of opposite divided by its identical value for adjacent is going to be equal to a value of 1. Okay, because it's an isosceles triangle. Rise over run, same, equals 1 when you divide them. As the angle starts to get larger, so we get up to say 72, and again this is an approximate diagram, but what do you notice about the relative lengths of the rise and the run? Well, the rise, or as we're now calling it the opposite, is starting to be much longer than the run or the adjacent. And so as this value overcomes this one, a large number divided by a smaller number is always going to result in a number bigger than 1. Now as we approach 90 degrees, that rise value gets to be really, really big. I'm going to go like to 89 degrees. Bear with me. And you can appreciate that this is really, really big and this is really, really small. So it's getting closer and closer to a big number. In fact, if you put in tangent of 89, you'll find you get 57. Okay, that's dramatically larger than 3, which is the value of the tangent ratio we had for 72 degrees. It's getting bigger and bigger and bigger. But once you get to 90 degrees, you have a rise that can go on and on and on forever, but you have no run because you're just going straight up for 0. So your rise value can be a really, really big number. Your run value is going to be 0. Well, anytime that you try to divide by 0, you're always going to get an error because it's impossible to divide something into no parts. Okay? So it's a good thing that we discovered that. All right. Next video next time.